Hello one and all, welcome back to Under the Hood of Python, a guide for complete beginners. In this session, we are going to take a look at the important and surprising floating point arithmetics in Python. Followingly, we are going to take a look at the ways to circumvent such flattening arithmetics. And then we are going to introduce you into a new concept in Python called as modules. And then we are going to take you through decimal modules and fraction modules in Python. Okay, we in our previous lecture took a look at the division operation. For example, when we divide 6 divided by 2, we get an answer of 3.0, which is a floating point quotient value. We also have 2 / based operation, which results in an integer result. For example, let's say we are going to divide 7 by 2, we will see the result as 3.5. Whereas if we are going to divide by using 2 different slash, we are going to see the result as 3. What is this? It simply truncates the decimal part of the number and converts it into an integer. This way of dividing the value was followed during Python 2. Whereas in Python 3, this is the convention of following the division operation. And the result of the division operation is always a floating point number. We have another operator in Python apart from regular division operator, and it's called as modulus operator. How does this modulus operator behave? Let's take a value called 100 and use this modulus operator and use another integer value called 2. We see the remainder as 0. What does it mean? It simply means that dividing 100 by 2 yields the remainder as 0. So that means modulus operator returns the remainder of a division operation. Let's say we are going to divide 51 by 2 using modulus operator, then the remainder value or the result of the modulus operator is 1. Similarly, if we are going to divide 33 by 10 or between 33 and 10, if we are going to use the modulus operator, we're going to see the result as 3, which is simply nothing but the remainder when 33 is divided by 10. Let us now take a look at some of the arithmetic operation between floating point numbers. Let's say I'm going to add 0.1, which is one of the floating point values, and 0.2, which is another floating point value. We're going to see the result as 0.3000004. Fair enough. Let's say I'm going to add 0.1 and 0.1. We are going to see the result as 0.2. Now, let me try to do this operation. 0.1 plus 0.2 equal to 0.3. What we are trying to do here is we are trying to compare the result of addition of 0.1 and 0.2 with 0.3, and the result is surprisingly false. Reason being, 0.1 plus 0.2 does not yield a value which is absolutely 0.3, or the value which 0.1 plus 0.2 yields is somewhere closer to 0.3 but not absolute 0.3. And that's the reason we get the return result of 0.1 plus 0.2 compared to 0.3 as false. Why does this happen? It happens purely because the floating point values in Python are represented in base 2 for the efficient computation on the hardware. How do we circumvent such arithmetic surprises when using floating point numbers? Definitely we need some methodology to overcome this, as these look something unconventional or it goes against the conventional mathematical principles. Okay, here we go. We have some 3 mechanisms to do that. One is by using a function termed as round function. The second one is using a decimal module in place of the default floating point values. And the third category is usage of fraction modules. Let us take a look at each of them in detail. At first, let us take a look at how does round function behave. Round function takes the first argument as a floating point value, or it takes an expression which results a floating point value. Let us see both of those examples. Let's say I have 0.234 as my first argument and apply a function called round. It just rounds it off to 0. So the second argument in the round function comes in handy to protect the value. Let's say for the same value of 0.234, I'm going to pass the second argument as 2. All it means is persist the 2 decimal places after the decimal point. Here we go. We're going to see the result as 0.23. Similarly, if I'm going to use 0.237, and again I'm going to say that round it off to 2 places after decimal point, we are going to see the result as 0.24 instead of 0.3. Okay, this is also true when the value of the floating point number is greater than 1. Let's say I have 2.365 or 356 and ask it to retain the first 2 places after the decimal point. We're going to see the result as 2.36. Similarly, we can also pass the first argument as an expression to the round function. For example, I'm going to pass it as 0.15 plus 0.25 comma 2, and we're going to see the result as 0.4. Now, let us try to use the same expression that we used for comparison in the previous example, that is 0.1 plus 0.2, and round it off to 1 decimal place after the decimal point, and then compare it against 0.3. In this case, we are going to see the result as true. But the problem of using the round function in most of the cases are the accuracy takes a backseat. What do we mean by that? Let's say I'm going to use the round function and pass the argument as 1.136547 as the first argument. Followingly, if I'm going to say, okay, round it off to 2 decimal places, I'm going to see the result as 1.14, wherein my accuracy is lost, and in many cases we need that accuracy to make right decisions. To overcome the accuracy loss that happens in round function, we use a new module called as decimal module and replace the fraction values with the decimal values. By the way, what do we mean by a module in Python? Let us have a quick look at it. Go to a location where your Python is installed on your computer. You would find a list of folders something like this. Get into a folder called lib, and inside that probably search for one of the files called statistics.py. Just try to open that file with whatever the program you have in your computer, and then we are going to see some details in this file. Let me try to search for something called as statistics, or I could even search for mean. Mean is one of the functions that is provided by the statistics.py file. So in general, the statistics module when imported provides a function called as mean to be used by our program. And hence we can term module as one or more Python files that are present in our Python environment, which helps us in providing some set of functions to be reused in our current program. Okay, with this understanding of what modules are in Python, how are they going to help us in our programming, let us now get into details of how do we use those modules in our program. Okay, we also realize that usage of decimal module will help us to circumvent surprises seen in the regular floating point arithmetics. So let us now get into the programming of how do we use decimal module in our code. Okay, before we use any specific function, we first need to import that specific module to our Python program. How do we do it? We're going to use a keyword called from followed by the module name. What is the module that we are going to use in this program? We are going to use a module termed as decimal. From module name decimal, I'm going to import a specific function called decimal. Okay, we can do this in two ways. We can import all the functions instead of just decimal from the decimal module. Or if we are going to only use the decimal function in our program, we can just import that specific function. Let's say as per our previous understanding of modules, if we had to use mean function from statistics module, what we would have done was from statistics, we are going to import a function termed as mean. So this is a way in which we are going to use a module and a specific function in the module. But for our program, we need a module termed as decimal and the function decimal in that module to be used in our program. Okay, let us now execute this cell and we must not see any kind of error. Now let's proceed ahead and create a decimal number as shown below. Let me print the created decimal value. Now how do we create a new decimal value? I'm going to simply use this function called decimal, which starts with capital D, and I am going to use a number, a floating point number, which gets converted into a decimal number and prints it out here. Okay. Before I get into the details of the decimal and its precision and much more about it, I want to also let you know some specific variable names or function names or how do we use them in our Python program. Let's say I'm going to create a variable called number and assign it a value 100. I can only use that number with the same case sensitivity. That means if I'm going to print this number with lowercase number, then I'm going to see the result. What happens if I by mistake capitalize it and try to see the value? No, because I capitalized n, it says that the number with capitalized n is not defined. So that means Python programs are case sensitive. Why did I say this point is, instead of using capital D followed by decimal, if I am going to use lowercase decimal, then I'm going to see a similar error. Decimal is not a function that's defined in the program. So be cautious to define the function name as is in your program. Okay. With these details about the case sensitivity in Python programming, let us now get back to our decimal function. Okay. Before we proceed ahead further, let us import another function termed as getContext from the same decimal module. How do we do it? We are going to use a from keyword followed by the module name. Followingly, we are going to write import function termed as getContext. Okay. Let us run this cell. We must not see any kind of error by running this cell. By now importing the decimal function and getContext function, it becomes completely available to our Python program. we can anywhere use these functions in our program. Fair enough. Let us now see what is this getContext going to do. Let us simply call that function called getContext and see what is its response. Here we go. It says that the context or the current context is having a precision equal to 28 and some set of parameters called as emin, emax, capitals, clamp, etc, etc. We are not going to get into details of each of these parameters. What is very important for us at this stage is the key or parameter termed as PREC or precision. Let us set that precision to a different value. Before which, let us try to create two decimal numbers and do a addition operation. Let us first initialize two numbers that will be used for addition operations. Here we go. We are going to use the decimal function followed by the floating point number to get it converted into a decimal value. We have two numbers called num1 and num2. Now we are going to calculate the sum of decimals simply by using a plus operator. And let us now try to print the result of it. Sum of decimals. And we are going to see a result wherein the precision goes for a very long value. That is the decimal part as well as the non-decimal part. I mean 567, which is the integer part, followed by 438, so on and so forth, which is the decimal part, together is called as precision of a number. So the precision of a number is 3 plus these many digits. Okay. Let us now set the precision for this context in such a way that we want precision up to 5 values. How do we do it? We can call this function called getContext dot PREC equal to 5. After we do this, let's say if we are going to recompute the sum of decimal values and try printing the same result set, we must see the precision being set to 5. That means the total length of the decimal number is now 5. Let us now proceed ahead and modify one of the numbers in such a way that taking a difference between the two numbers must yield a value less than 0. Okay, let us now fixate the number, one of the numbers which is number 1 or num1 equal to a value equal to 443.12243. And now let us take the difference of decimals as num2 minus num1. And now let's try to print the result of decimal, which is nothing but the computed difference in decimal numbers. And if we see here, the total length of this decimal number seems to be of 6. That is, the number of digits or the total length of this decimal number seems to be 6, but ideally it is correct. How is it so? The 0 which is present before the decimal number is always ignored and is not counted for the precision of the number. So that's the reason we are going to see the precision of this number being 5, and we see that there are 5 values which are present after the decimal point because the value which is present before the decimal point is 0 and is not considered as part of the precision. If you remember right in our floating point discussion, we realized that we had an upper cutoff or max limit for the value that could be defined for a floating point value. If you remember right, it was 2 to the power of 1024, right? Let us see if we can circumvent the same using decimal function or a decimal number. Before which, let us try to increase the context precision to 15 by using this statement and execute this cell. Now let's try to reiterate the same example what we saw for a floating point number. 2.0 is a floating point number and increase its exponent value to 1023. In this case, we are not going to see any error and we are going to see the result successfully. If we now try to increase the exponent's value by 1, which is nothing but 1024, we are going to see an error as result is too large for a floating point number. Okay, how do we now circumvent this? Instead of creating a 2.0 as a sample or a standard floating point number, let us create a new decimal value of 2.0 and assign it to a variable called val. And execute this cell. We see again the same error. Sorry for it. Let us rename to a write function. Okay. Now let us try to raise this to the power of 1024. In this case, we are not going to see the error anymore. Instead, we were able to bypass the upper cutoff which was set by the conventional or the regular floating point number. So by using a decimal number, we are able to successfully get rid of the max size that is set by the regular floating point number. Okay. With this understanding of what is the behavior of decimal and its usage, let us now get into the last module of our coding lecture, which is nothing but fraction module. Why do we need fraction module and how do we use this? This comes in handy when we do not want to convert the fractional value to a decimal or a floating point value. Instead, we want to compute the operation between two fractional numbers. Let's see what do we mean by that. Before which, let us import fractions function from fractions module. From fractions, import fraction function. So we are now going to import fraction function from fractions module. After the successful import of fraction function, let us take a look at how can we define fraction numbers. Let's say I'm going to create a number called num1 using fraction function, and within the fraction function we are going to pass two parameters. The first parameter being the numerator of a fractional number and the second parameter being the denominator of the fractional number. Let's execute this cell and try to print what's there in num1. Now we are going to see the result as 1 divided by 3. Similarly, let us create another number called 2 divided by 3 using the same fraction function and passing two arguments, the first argument being the numerator, second argument being the denominator. And if we are going to print the same, we will see the result as 2 divided by 3. Similarly, let us create another number termed as num3 using the fraction function and pass the two arguments as 4, 3. Now let us try to compute the sum of all these three numbers, num1 plus num2 plus num3. Summation of all the three fractional numbers yields the fractional result. The same computation if we do directly without converting it into a fractional number, let's see what the response is. 1 divided by 3 plus 2 divided by 3 plus 4 divided by 3, we are going to see the result as 2.333 recursively going. So that means if we are going to compute it this way, it is simply the computation of sum of floating point numbers. Whereas if we are going to convert each of the number into a fractional number using fraction function, then the summation is nothing but the sum of fractional numbers yielding another fractional value. Before we wind up the lecture with a session overview, let's have a quick look at how do we represent complex numbers in Python. Complex numbers, what are they? This will be something which is very familiar to the people who are very much enthusiastic in mathematics. Here we go. In Python, we represent the complex numbers in the form of x plus yj, where x and y are the integer or numeric values and j or I is nothing but a complex numbers value which is equal to root of -1. And we are going to represent it in this format, 3 plus 4j. And this is in the form of x plus yi or x plus yj. Let us find what is the type of this number using the type function and pass the entire value to it. We want to see the type or the return value or return type of this 3 plus 4j is nothing but complex. We can also define a complex number using a function called complex and pass two arguments, one being x and the other being y. That constructs again a complex value of form x plus yj. Fair enough? Let us now create a simple variable termed as c and assign a value called 10. If I ask you, is this number a complex number or not? The answer is yes. How do we say this is a complex number? Here we go. Every complex number has two parts in it, a real value and an imaginary value. In the equation x plus yj, the real value is termed as x and the imaginary value is termed as y. Let's now create another variable called c1 and assign the same value 3 plus 4j to it and find the real portion of c1 which is equal to 3 and the imaginary portion of c1 which is equal to 4. Okay. Similarly, let us go back to the variable c which is pointing to an integer like object called as 10 and find is there any real value for it? C.real, yes, we get the real value as 10. What is the imaginary value then? Imaginary value is nothing but 0. So we can represent 10 as 10 plus 0j, which turns out to be a number or a value which is pretty much equal to a complex number. So in general, any number can be represented as a complex number, but it uniquely defines a complex number when we have it in the form of x plus yj. With these details, let us wind up our long lecture by having a quick recap of what we did in this session. First of all, we took a look at surprising arithmetic operation using floating point numbers. Followingly, we got ourselves introduced into what are modules in Python. And then we took a look at how do we circumvent some of the limitations that we see in case of floating point numbers using two functions termed as round and decimal. Followingly, we took a deeper understanding and details of what are decimal and fraction modules and how do we use it. Finally, we had a quick glimpse of what are complex numbers and how do we represent them using Python. Up next, we will get into a GPA calculator project in which we are going to implement all of these topics which we discussed till now. Till then, take care of yourself, have a great time, see you in the next lecture.